Hello there and welcome to section 11.3 on calculus with polar coordinates. And so to begin, we're going to look at how we can compute the derivative dy dx for a curve given in polar form. Okay, so looking at the first question on the worksheet, it says suppose a curve has polar equation r equals f of theta. Okay, and so to illustrate here, we'll consider this equation r equals 2 cosine theta. And as we saw in the last section, this describes the circle of radius 1 centered at the point 1, 0. Okay. Now part A says describe this curve using parametric equations. Okay, so the idea here is that first off, for any point P on our polar curve, right, if this rotation angle is theta, then this radial distance from the origin out to our point R is described by f of theta. So in the case of the circle here, okay, if we rotate through this angle theta, okay, then this corresponding point P on our circle is a distance of 2 cosine theta from the origin. Okay, so now to write a parametric representation for this curve, we're going to go back to those relationships between polar coordinates r theta and Cartesian coordinates x, y. So recall that x is r cosine theta, and since this radial distance r is described by f of theta for points along our polar curve, r cosine theta can then be written as f of theta times cosine theta. Likewise for y is r sine theta, and so this is equal to f of theta times sine theta. Okay, now in section 11.1 on parametric curves, we typically use the letter t for our parameter. Okay, so here we're just treating the rotation angle theta from polar coordinates as our parameter. Okay, so now for this particular circle equation, all right, so we can write down a parametric representation as follows. So x is r cosine theta, and since here r is 2 cosine theta, this is 2 cosine theta times cosine theta, and that of course is just 2 cosine squared of theta. Y, that's r sine theta. And again, since r is 2 cosine theta, this is 2 cos theta times sine theta. All right, cool. So now, before jumping over to part B, let's go ahead and look at this on Desmos. So here at the top, I have the polar equation, r equals 2 cosine theta. And see this, the circle of radius 1 centered at the point 1, 0. And then here I have the parametric representation. And remember, Desmos likes t specifically for the parameter, but we're really just thinking of the parameter t as this rotation angle theta from polar coordinates. And so you see 2 cos theta, that's our r, times cos theta, and then 2 cos theta, that's our r, times sine theta, that's our y coordinate. So if I turn that on, you see it's exactly the same thing as our green polar curve. Okay, and then down here I just have a slider. Allows me to add in this tracing point for my slider A, and there you have it. Cool. All right, now looking at part B, it says derive an equation for the slope of the curve dy dx using your equations from part A. Well, for this, we're just going to rely on what we already done back in section 11.1. So recall dy dx, this was just the ratio of our vertical velocity, dy dt, to our horizontal velocity, dx dt. So for a polar curve, where again we're thinking of the parameter t as the rotation angle theta, right? dy dx then would just be dy d theta divided by dx d theta. And since I now have these expressions for x and y up above, I can go ahead and differentiate those with respect to theta, and I'm going to have to use the product rule. Okay, so for dy d theta, well, I'm going to take the derivative of f, and that's going to give me f prime of theta, and then multiply that by sine of theta. And then I'm going to add to that, okay, f of theta times the derivative of sine, and that's cosine theta. Okay, so this expression is dy d theta, and that's our numerator. Okay, down in the denominator, dx d theta, do the same thing. Now we're going to differentiate f of theta times cosine theta. So you're going to get an f prime of theta times cosine theta. And then you're going to get a plus f of theta times the derivative of cos, and that's going to give you a negative sign, so we get minus f of theta sine theta. Okay, so this, although it is a bit messy, right, it gives us an expression for dy dx in terms of the parameter theta. Okay, so let's apply that over here. Okay, so for dy dx, I'm going to differentiate first y with respect to theta. And so to differentiate this, I'm going to use, again, the product rule like we just did. So I'm going to get the derivative of 2 cos, well, that's negative 2 sine, and then that's going to multiply that sine to give me negative 2 sine squared of theta. Then I'm going to add to that 2 cosine times the derivative of sine, and that's going to give me a 2 cosine times cosine, so that's plus 2 cos squared of theta. All right, now downstairs we have dx d theta, so I have to differentiate 2 cosine squared of theta. So I can use the chain rule here. That's going to be 4 cos theta. So that's your 4 cos theta times the derivative of the cosine from the chain rule, and that's negative sine theta. Okay, now I can clean this up a little bit using some identities, so we'll do that. Now up in the numerator, recall that cos squared theta minus sine squared theta, that is cosine 2 theta. So if I factor this 2 out, I have a cos squared minus sine squared there, so this is 2 times the cosine of 2 theta. And then likewise downstairs, 2 cos times sine, that's sine of 2 theta. And since I have a 4 cosine, that's, well, 2 sine of 2 theta, and there's that negative out in front. And so now to simplify this, the 2's drop out, the negative's out in front, and cosine over sine is cotangent, so I get negative cotangent of 2 theta for the final expression. All right, great. Well, that's going to do it. We'll pick up with more of this in the next video. Thanks.